Okay, so today we are going to first of all prove this thing that we have so far been unable to do, and then if we have time, we will go to the theory of infinite series. At least we will introduce the thing, chapter 7. Now recall that we have so far been unable to prove this because the way we were proceeding that required us to extend a limit like this. We have already seen this, I think, twice at least, from rational values of sigma to real values of sigma, and we have been unable to do that. So that way is blocked for us. But then in yesterday's video towards the end, I said that one can in fact make things work even without that extension, circumventing that extension. And the idea in fact I have come across on an online mathematics forum. But today, a few hours ago, while I was going through these things, I realized that there is a gap in that idea also. They messed up, consequently here I messed up. So that means in that way we cannot go actually. In fact, now I believe that if one goes like how we were going, such an extension becomes absolutely necessary. So I then started thinking what then can be done. And luckily I remembered that unlike how we have defined these powers of real numbers where the exponents are also real using sequences, we have defined such a power, right? There is another way of doing this which does not use sequences but which uses supremum of a set of real numbers. So that's what we are going to do, and luckily in that way we can get the proof. It becomes a little messy, but what can we do? We have to get the proof. That's the thing. So what we are now going to see here, it will be different from what we have been doing so far. So here is the claim. So what we are first going to do is this. We will claim something, we will then prove the claim, and then we will use the claim to get this result in some steps. So this is the claim. Let x and t be real numbers such that x is greater than 1 and t is greater than 0. Then our claim is this: x to the power t. We already know what x to the power t is. Okay, using the sequence definition we know what it means. Now our claim is that this is the supremum of this set whose elements are x to the power alpha, where alpha is a rational number and alpha lies between 0 and t in this manner, strictly lies between 0 and t. So let us now see the proof of this claim. But before we see the proof, let's just notice one more thing, that this set is a non-empty set of real numbers. That is because we have in fact already seen in the previous sections somewhere that we can find a rational number alpha satisfying these inequalities, and that's because t is greater than 0. So there will be some rational number sitting strictly in between 0 and t. So that's why the set we see here is a non-empty set. Now what do we need to show? We need to show two things. First of all, that x to the power t is an upper bound of this set, that it is greater than or equal to all the elements of this set, and then that it is the least upper bound, it is the smallest among all upper bounds, which is equivalent to showing that no real number less than x to the power t can be an upper bound of this. If you manage to show that, then combining that with the fact that x to the power t is an upper bound, this will make you conclude that it is in fact the least upper bound, supremum of this set, proving our claim. So we start off by supposing that this is not an upper bound. Suppose this is not an upper bound of, it will be somewhat cumbersome to keep writing this set, so let's give it a name. Let us call it S. Then being an upper bound means being greater than or equal to all x to the power alphas. Not being an upper bound means at least one x to the power alpha is not less than or equal to x to the power t, it is strictly greater. Then this is greater than x to the power t for some rational number alpha satisfying this. Okay. Now what now we are going to do, in order to use the definition of x to the power t, we need a sequence of rational numbers converging to t, because then the limit of x to the power, the terms of that sequence will be x to the power t by definition. So what we do, we consider a sequence like this. Now let alpha n be a sequence of rational numbers in the open interval 0, t converging to t. It seems plausible that such a sequence can be found, but one may of course ask exactly how. How are you assuming that you can have such a sequence? And the idea basically is this: this is your open interval between 0 and t, right? So what you do, you need to have a sequence of rational numbers lying in this open interval, and that is converging to t. You consider one half of this open interval, and in fact without first of all considering one half, because that will not serve any purpose, what you first do, you know that there is a rational number lying between 0 and t, so you choose one such rational number alpha 1. Now this alpha 1 may or may not be greater than t divided by 2. whatever the case, I mean, alpha 1 may either lie to the left of t divided by 2, or it may be equal to t divided by 2, or it may lie to the right of t divided by 2 also. Whatever the case is, you can then consider the open interval this beta comma t, where beta is the maximum of alpha 1 and t divided by 2. So the I mean, whatever we have drawn here, according to that, beta is equal to t divided by 2 here. If alpha 1 lies on that side, then beta will be equal to alpha 1. So whatever the case is, now our new open interval is this, and in this new open interval, what you do, you then again will have another such rational number alpha 2, and then you consider beta prime to be the maximum of alpha 2 and t divided by 4, and then consider the open interval beta prime comma t, and continue this process. This will give you a sequence of rational numbers, recursive sequence. Recursive sequence means the definition is recursive. Each term of the sequence, its choice depends on the terms that have been chosen previously, a recursive definition. And it's pretty easy to show that this sequence will converge to t, because the intervals are shrinking more and more, and the intervals themselves are getting closer to t. That is the purpose of these things, t divided by 2, t divided by 4. You can easily do this on your own. If someone asks you to rigorously prove that yes, there is such a sequence, then you can construct a sequence like this, and you can prove that that sequence converges to t. So we are not going to do that because it's understood, and we just simply assume that such a sequence can be chosen. Now we are going to use this sequence. The next thing is this: since limit of x to the power alpha n as n approaches infinity is x to the power t, we can choose a real number epsilon greater than 0 such that x to the power alpha does not belong to this open interval. Now what is all this? Because our alpha n is after all, it does not matter where it has come from, but after all it's a sequence of rational numbers converging to t. So by our definition of x to the power t, we have this limit, and because we have this limit, oh wait, I have written things in a slightly messed up manner. This is not coming from here, okay, sorry. This is coming from the fact that x to the power alpha is greater than x to the power t. That's why we have this. It's like this now. We have x to the power t, and we have x to the power alpha here somewhere. So what we have done, we have chosen an epsilon that is small enough such that this open interval does not contain x to the power alpha. In fact, to be a little specific, you can take epsilon to be half of this distance. This epsilon will work. But since we are not going to use any specific value of epsilon, the fact that such an epsilon exists is good enough for us. Now that limit thing will come. So note that x to the power alpha not being in this interval really means it is lying to the right of the interval, and that is because x to the power alpha already lies to the right of x to the power t. Now since limit of x to the power alpha n is equal to x to the power t, there exists a positive integer n such that x to the power alpha n belongs to this open interval for all n greater than or equal to capital N. It may seem a little strange, but this entire statement is equivalent to your more familiar statement involving distance. The distance between x to the power alpha n and x to the power t is less than epsilon for all n greater than or equal to n. This and this, they mean the same thing. Okay, now this entire thing has consequences. What will now happen to this x to the power alpha n's and x to the power alpha? Because x to the power alpha lies on that side and all these x to the power alpha n's are inside this, so all of them are forced to be strictly less than x to the power alpha. Hence, x to the power alpha n is less than x to the power t plus epsilon, which is less than x to the power alpha for all n greater than or equal to n. Now forget about this intermediate real number x to the power t plus epsilon. Think of only these two, x to the power alpha n and x to the power alpha. X to the power alpha n is strictly less than x to the power alpha for all n greater than or equal to capital N. So by lemma 569, what is that part? Part E, we have alpha n strictly less than alpha for all n greater than or equal to n. Keep in mind that our alpha n's are rational and our alpha is also rational. So we have been able to use lemma 569 part E. And there is one more thing. This part requires the base x to be greater than 1, and that is why here we have x greater than 1. So we now have this. Hence, t is equal to limit of alpha n is less than or equal to alpha which is less than t. Wait, alpha is less than, yes, because alpha is coming from this set. No, x to the power alpha has been chosen from this set that according to our supposition is greater than x to the power t. So alpha itself is less than t. Now here there is a subtle thing which also I should point out. These inequalities don't say something about the entire sequence alpha n, but rather this subsequence. All the terms of this subsequence are strictly less than alpha, but because the original sequence converges to t, this subsequence also converges to t, and what we have used here is the comparison principle. And in fact, let us just write that. And because of that comparison principle use, in place of this inequality, this strict inequality, x to the power alpha n less than, well, we are not there, we are here. In place of this strict inequality, we have replaced that with less than or equal to. We can write by the comparison principle. And this is a contradiction because t is strictly less than t. This is a contradiction and hence our supposition is wrong. That means x to the power t actually must be an upper bound of capital S. Is an upper bound of capital S. Next, we are going to show that it is the least upper bound. So here again, we will suppose that there is an even smaller upper bound, and again derive a contradiction. Suppose some real number y less than x to the power t exists that is an upper bound of S. Okay. Then we are again going to use that sequence which we chose previously, which lies in this open interval, and we are going to use the corresponding powers. Then x to the power alpha n, because we have supposed y to be an upper bound, so x to the power alpha n will be less than or equal to y, which of course is less than x to the power t for all n greater than or equal to 1. These inequalities are true for all n because all these x to the power alpha n's are actually elements in this set capital S. Now what can we possibly do with these inequalities? This implies again we can take limits throughout these inequalities, and doing so we get again using the comparison principle by the comparison principle. So now we have got the contradiction that x to the power t is less than x to the power t. Which is a contradiction. So our last supposition is wrong, that is, no such y exists. So no y less than x to the power t can be an upper bound of capital S, but x to the power t has already been proved to be an upper bound of capital S. So that means it is the least upper bound, hence the claim. Okay, now we are ready to use this claim to prove the result. In order to be able to use this claim, first of all we will assume that our x is like this x is greater than 1, and then we will handle the case x less than 1 separately. Several cases will occur, but the further we go into the proof, the shorter things will get. Okay, so now proof of that above identity. First, assume x to be greater than 1, and in this case too 4 cases will appear, depending on the signs of q and r. You can of course see that there is no point in taking one of these equal to 0, because in that case both the sides are trivially equal to 1 by definition. So none of them is 0, so each one of them is either positive or negative. Let us first assume that q is positive and r is also positive, right? Now here there is again a claim. We now claim that, let me write it there, x to the power q whole to the power r is equal to the supremum of this set x to the power alpha beta such that alpha and beta are rational numbers where both of them are positive and alpha is less than q and beta is less than r. We are now going to prove this claim. Much like how we proved this claim, we will show that this is an upper bound and then that this is the least upper bound. Suppose this is not an upper bound of, again here also let us give this set a name. Then at least one element of the set will be strictly greater than this. This is greater than x to the power q whole to the power r for some alpha and beta belonging to the set of rational numbers satisfying these inequalities. Okay, now what can possibly go wrong? Now we want something to go wrong. Now recall the definition of this, but not the old definition using sequences. You use this claim with x to the power q in place of x and r in place of t. Then, or let me, for the sake of clarification, clarity. For the sake of clarity, let me just mention what this thing is actually, like this. Since this is equal to the supremum of, by our previous claim, x to the power q whole to the power alpha, where alpha is a positive rational number less than r, we have don't write x to the power q alpha without using brackets, because that is an entirely different thing. So we have that means what? Because this is the least upper bound of this set, so this real number is greater than or equal to all elements which look like this. In particular, because our beta is a rational number satisfying this inequality, this will be greater than or equal to x to the power q whole to the power beta. So combining everything, we have this x to the power alpha beta, which itself can be written as x to the power alpha whole to the power beta. This is greater than x to the power q whole to the power r, and that is greater than or equal to x to the power q whole to the power beta. Note one thing, that we have used the version of this identity for rational numbers here in this step. That is already available to us. We already have that in lemma 5, 6, 9. And we are not mentioning that because that's understood. Here both alpha and beta are rational numbers, so we can do that. Now look at the first term and the last term among these terms. X to the power alpha whole to the power beta is strictly greater than x to the power q whole to the power beta. And we are now in a position to use another part of lemma 5, 6, 9, part D. Which implies that here the exponents are the same but the bases are different. That x to the power alpha is strictly greater than x to the power q. part D is that thing which tells us that if Q is a positive rational number and X and Y are also positive real numbers such that X to the power Y, X is greater than Y, then this implies X to the power Q is greater than Y to the power Q, and conversely also. So in place of Q, here we have beta. Keep in mind that our beta is positive because beta is coming from the set capital T, where all these exponents we have chosen to be positive in order to be on the safe side. So this implies this. In place of X, we now have X to the power alpha, and in place of Y, we have X to the power Q. Okay, but now we have got a contradiction. This is a contradiction because X to the power Q is, according to our claim, the supremum of this set. And X to the power alpha belongs to this set. So because it's an upper bound, supremum means in particular it's an upper bound. Least upper bound, fine, but after all an upper bound. So X to the power Q should have been greater than or equal to X to the power alpha. However, we have got this. Don't lose track of what is going on, okay? Alpha originally, just like beta, is coming from our set capital T, and you will see in the definition of T that alpha satisfies these conditions, just like beta also satisfies these conditions. The only difference is that for beta, here in place of Q you have R. So our last supposition is wrong, that is this must be an upper bound of the set capital T. Next we have to show that it's the least upper bound. The strategy is same like before. Next, let me use some ink, will be more prominent. Next, suppose there exists a real number z less than x to the power q to the power r, that is an upper bound of t. this place is so confusing that I have to really carefully see what I am doing and then write. Okay, then the fact that we have supposed z to be an upper bound of t will now simply mean this. Then z is greater than or equal to all the elements of t which look like this: x to the power alpha beta for all rational numbers alpha and beta satisfying these inequalities. Less than r, this is not q. Okay, now what? Okay, so this is what it means for z to be an upper bound of t. But you look at this inequality also. This inequality says that z is less than this thing, which itself is the least upper bound of some set, from z less than x to the power q to the power r, which by this above claim is the supremum of this set x to the power q to the power say gamma we conclude z is less than the least upper bound. So z itself cannot be an upper bound of this set. We conclude that z is not an upper bound what is the this is r, hence so that means at least one element of this set will be greater than, strictly greater than z. For some rational number gamma satisfying this. Hence, or this implies x to the power q whole to the power gamma is greater than z, but z is an upper bound and we already had one conclusion for that, upper bound of that z. So this is greater than or equal to this, and this of course we are going to, okay, let us just first write the general statement for all rational numbers alpha and beta satisfying now. Note one thing, that because this is true for all such alpha and beta, we can now choose alpha and beta according to our needs. In particular, do you see that you can choose gamma in place of beta, because gamma is a rational number and gamma satisfies these inequalities just like beta. So in particular, x to the power q to the power gamma is greater than z, and that is greater than or equal to x to the power alpha gamma. And because alpha and gamma are both rational, so by the rational version of this result we have this. And keep in mind that here alpha is anything like this for all alpha belonging to q satisfying this. That is, we can still modify it a little bit more. X to the power q whole to the power gamma is strictly greater than z to the power 1 over gamma whole to the power gamma. Because gamma is a rational number and gamma after all is greater than 0, so 1 over gamma is also a rational number and that is also greater than 0. It does not matter that they are greater than 0. What now matters for this particular step is that by the rational version of this, because both 1 over gamma and gamma are rational numbers, this thing will be equal to z, because this is equal to z to the power 1 over gamma times gamma, and this is greater than or equal to x to the power alpha whole to the power gamma for all alpha for all rational numbers alpha satisfying these inequalities. So again, now here we can use our this lemma 569 part D. So we can get rid of the exponents gamma and we have this x to the power q is strictly greater than z to the power 1 over gamma, which is greater than or equal to x to the power alpha for all alpha belonging to q satisfying this. Hence, okay, so now what do we see from these inequalities? It seems that we have shown z to the power 1 over gamma is an upper bound of a set. So we have this is greater than z to the power 1 over gamma. It is greater than or equal to all elements like this. So that means this is an upper bound of this set of all x to the power alpha, that is this set, where in place of t you have q. So this will be greater than or equal to the least upper bound of this set, that is supremum of this set. Zero less than alpha less than q. But according to our claim, this set is nothing but x to the power q, and this is a contradiction. X to the power q is greater than x to the power q. This is a contradiction and shows that no such set exists. Hence, x to the power q whole to the power r is in fact the least upper bound of capital T, and which, just for the sake of seeing what T is or what T was, how it was taken, T is this. Okay, now we are going to use this claim. I told you it's going to be messy and big. Okay. So let's write in a new paragraph. For any rational numbers alpha and beta such that these inequalities are true, alpha beta is a rational number satisfying this. Alpha and beta are positive, so their product is also positive, and their product is less than QR. Hence, what? We have seen this claim for quite a while now, so let's just wrap this place off to create space. Hence, x to the power alpha beta, that is our capital T, in other words, is a subset of this set x to the power, say what can I take, say delta, or let me just take omega, say. So that means the least upper bound of this set is greater than or equal to all the elements of this set, and hence, because this is a subset of this set, that least upper bound is also greater than or equal to all these elements in particular. In other words, the least upper bound of this set is an upper bound of this set as well. This implies there is no point writing this again, so let's just recall that this is T. This implies, and the least upper bound is what by our claim, first claim, x to the power QR. This is some upper bound of T. So this will be greater than or equal to the least upper bound of T. Thus, is greater than or equal to supremum of T, which is this. So we have got one inequality. Now we will get the other. Conversely, it's better to stick to the Greek letter or whatever letters I have used here, because it's very easy to make mistakes in this extremely complicated situation. Conversely, let delta be a rational number such that delta lies between 0 and q bar. So rationals like what we have here, like omega. And we don't need this also. Then keep in mind that our q and r, our original real numbers, we chose to be positive. We are in that up case. We are still in that first sub case of that first case where x is greater than 1. So q is positive. So because q is positive, we can divide throughout by q without altering the direction of the inequalities. So we have this delta divided by q less than r. So there exists a rational number which is what I have taken mu. Such that mu lies between delta by q and r. Again, using that fact that between any two real numbers, we can strictly, in between them, we can find a rational number. And then there is still more. Another rational number now must be chosen. From these, we have what? Okay, now what we do is we multiply throughout by q and we divide throughout by mu. That we can do because both q and mu are positive. Q is already positive, but the way we have chosen mu is also a positive real number, a positive rational in fact. So we have 0 less than delta divided by mu, which is less than q. So again, there exists a rational number nu in between these two real numbers. Okay, so finally what do we have? Hence 0 is less than delta and delta is less than what? Nu mu. Okay, and nu mu itself is what? This is also less than something. because nu is less than q, nu mu is less than q mu, and q mu itself is from here less than q r. Okay, and nu mu is a rational number because both nu and mu are rational numbers, right? So now what do we have? You see, we have been able to find rational numbers nu and mu such that their product lies strictly between 0 and qr, and where are all the things? Mu is strictly lying between 0 and r, and nu is strictly lying between 0 and q. Shall we write this thing also? Yes, we should write, comma, nu is lying strictly between 0 and q, and mu is lying strictly in between 0 and r. Hence, x to the power delta is less than x to the power nu mu, which is less than or equal to the supremum of t, because you can see that x to the power nu mu is now an element in t. Nu satisfies these inequalities, mu satisfies these inequalities that beta satisfies, and both are rational numbers, and hence this is less than or equal to the supremum of t, which we have already shown is equal to this. So delta has been chosen to be any rational number like this, and that means this is an upper bound of this set, x to the power delta this is one upper bound, so the least upper bound of this set will be less than or equal to this upper bound. I just want to keep one thing though, so that you can see we have in fact got both the required inequalities to be able to conclude equality. Thus, x to the power q whole to the power r is greater than or equal to the supremum. This is one upper bound, so we are now going to take the supremum. It is the least upper bound. Which by our first claim is to the power qr. So we have proved x to the power q r is greater than or equal to x to the power q whole to the power r, and also x to the power q whole to the power r is greater than or equal to this. Therefore, this in the first sub case, but now the others will follow from this. Let's see how. The others are quick, and the reason for this quickness is part C. Recall that although we have this second identity, this is the second identity of part B in theorem 671 or lemma 671, I am not sure, I forgot. But we first proved part A, of course, and then part B, first identity is proved in the text, and instead of proving part B's second identity, after that we in fact completed the proof of part C, which follows from the first identity. So we can now use that part C here, and we won't even mention that we are using it. It's understood. Next, assume you can take any one of these. Q greater than R, Q greater than 0 and R less than 0. Then x to the power q whole to the power r. Using part C, this is equal to this. In part C, keep in mind what do we have in part C? X to the power minus q is equal to 1 over x to the power q, and we don't have anything about the sign of the real number q. In part C, q can be positive or negative, anything. So here also we don't have to bother about what R actually is, whether it is positive or negative. In any case, we can apply part C. So now you see that q is positive, minus r is also positive. So we can use whatever we have proved above. Using that, we get this x to the power q times minus r. Again you use part C, this becomes and that gives you QR. Next, assume Q to be negative and R to be positive. Then this is equal to using part C, we first get this. And this is equal to this. Question is how? We haven't seen this before, but it can be quite easily proved using just the definition of real exponentiation. And this that is what we are trying to say here is this. Say R is equal to 1 over y to the power r. Y, of course, is a positive real number. Showing this is equivalent to showing that if you multiply these two things, you get 1. and this you can show directly by using the limit definition and corresponding properties for rational numbers, which also may not be present, but you can prove that. I mean, you can come from the very beginning, natural number exponents, rational exponents, real exponents. You will see that, well, after natural numbers we have integers, and then rationals, then real. You will see that all the things, I mean the corresponding result for those type of exponents follow easily directly from the definitions themselves and elementary properties of real numbers. So that justifies this step. But now again, here q is negative, minus q is positive, and r is positive. So using this subcase, this is equal to minus q times r. And now again you can use part C. Note carefully one more thing though. Whatever we have shown, it works only when the base is greater than 1. And the base is greater than 1 means this x is greater than 1. So you can see that wherever we are using this subcase, here in these subcases, we are doing it for x and not for 1 over x. Okay, because for 1 over x we don't have this thing. We have this thing only for positive exponents and x greater than 1. X less than 1, that case is still, that is yet to come. Finally, assume that both q and r are negative. Then this is equal to, by using part C we have this. Now although q is negative and minus r is positive, but you now are in this case, and in this case we have already proved it. So we have this. You can in fact make this whole thing much more rigorous by writing all these things, that by that subcase we are in fact having this. So here we are not using this subcase, keep that in mind. Here we are using this subcase. So in this step we have done just that. And now again using part C, we get this. So that means our result has been proved for all q and r irrespective of the, regardless of their signs, but x greater than 1. So the next case, which is the only thing that is left for us to do, is to consider the case when x is less than 1. Now assume x continues to be greater than 0, but now it is less than 1. Then 1 over x is greater than 1, and so the result is going to be true for 1 over x in place of x. Now this implies whatever we said just now a while ago about bringing this exponent here, that continues to be true, and we can now use that thing. For this one we can do that in steps. For this one, however, we can do that directly. X to the power q r, and this implies, now here, bringing the exponent down over the denominator. That means here the denominator is x to the power q whole to the power r. And this equation implies, if you take reciprocal, x to the power q bar. So despite the fact that this proof is extremely messy, follows a different philosophy, a different route than what we were following in proving the other parts, and looks quite ugly, frankly, but it's a proof nonetheless. And now we can say that yes, we know that for sure that this happens, and it's over. I don't know how much more time I have, but let's just see some things from series. So the sequence things are finally over, this nightmare. Many more nightmares are yet to come. And one terrible nightmare is chapter 8, where you will see why. Hopefully we won't get stuck like this, but there are some pretty complicated things, specifically in the section involving order relations. That's why I said at one point while proving these things that these are the kind of things that people go through only once in their lives. They go through this, they see that everything is okay, and that's just it. They never come back. It is nothing interesting or anything. It is just something that is true and that is needed. It's useful. Okay, now we come to chapter 7. Series. Now that we have developed a reasonable theory of limits of sequences, we will use that theory to develop a theory of infinite series. But before that, we must first develop a theory of finite series or finite sums. Things which well in after okay. Mind has stopped working. Infinite series. After that, there is this expression of infinite series like this. We are varying. It does not matter what I write here, but let's just write what Tao has written. And so on. So this is the first section. Finite series. And this is the definition. Problems will start from the definition itself, because the definition, we will understand what it means, but the definition is there are some issues with the definition. It has not been written very carefully. And the actual definition looks like this. We will address these issues whatever we come across in the when we solve the exercises. Let m and n be integers. And let ai, where I varies from m to n, be a finite sequence of real numbers. What this really means is that this finite sequence is a function. This finite sequence is a function from this set of integers, m plus 1, etc., into the set of real numbers which assigns, I am using the sequence symbol itself to denote this function, which assigns the real number ai to the input I, which is coming from this set. That's just it. This is the finite sequence. Just like an infinite sequence has an infinite domain, and this set is the set of real numbers, a finite sequence has a finite domain. That's the only difference. Now, there is no problem with this, but then assigning of, so he has written this also. A real number ai to each integer I between m and n inclusive. That means taking those values also. It will take the values m and n I and also the integers in between, i.e. this. Then we define the finite sum or finite series which we denote by a symbol that looks like this. In reading this symbol, we say this: summation of ai as I varies from 1 m to n by the recursive formula. This is defined to be equal to 0 whenever n is less than m. That can happen. And I varying from m to n plus 1, this is defined to be equal to summation I varying from m to n plus a n plus 1 whenever n is greater than or equal to m minus 1. My problem with this definition is that we are saying that this is a finite sequence, okay, and we are saying these things which makes it seem like n is already greater than or equal to m, and then suddenly we are saying that this thing is 0 if n is less than m, plus we are defining things where we are mentioning n plus 1. Where is this an plus 1 coming from? An plus 1 is not defined here anywhere. So we will have to address these small issues with this definition. We will do this in the exercises. But before that, before I stop things, let us just write a few things that have been written by the author after this definition. And there is a still more subtle issue. We are saying that we are using a recursive formula for defining this. Usually when we use recursive formulas, they define a sequence which is not a finite sequence. We define infinitely many things. So exactly what is going on here? How are we using the principle of recursive definition in defining this definition? So that we will have to make clear. But now here we go. Thus, for instance, you get the idea what this says. If the upper number is less than m, then this symbol means 0. That's just it. Okay, it does not have any other meaning. And if the upper number is not less than m, then here the things are coming. Thus, for instance, we have these identities. Summation ai, where I varies from m to m minus 2, this is equal to 0. Then summation ai, I varies from m to m minus 1, this is also equal to 0 because of this thing, this part of the definition. Whereas summation I varying from m to m ai, now you can see that this m here is m minus 1 plus 1. Okay, m minus 1 plus 1, and that is the smallest possible value of n where we can start to use this part of the definition. So now by this part of the definition, this is equal to summation I varying from m to n, but our n is now m minus 1 plus what? n plus 1, that means am, and this is 0. This is equal to am, which is what we expect, because we think that this sum has only one term, I varies from m to m itself, so there is only am, and in fact the definition matches with our expectation. Two more are given, the next two. The next one will be what? Summation I varies from m to m plus 1. So now n is m in this case. So by the definition, this is ai plus am plus 1. But this we have already calculated to be am, so we have this. And one more, by using this part with the value n equal to m plus 1 this time. A m plus 2, this is n plus 1. Now this is this thing, so plus 2. After this, there are remarks involving these symbols and their meaning, some difference between the actual, this real number as opposed to the expression which looks like this, some semantic difference. These things will come, we will see in the next week, Sunday. And today is also Sunday, so coming Tuesday we have already gone through vector spaces last, right? So that means coming Tuesday let us do calculus. So that's just it. If you want to comment on these things, you can write in the comment section below, or you can mail me at my address, which will be there in the description of this video. So see you next Tuesday with calculus. Until then, this is me, Lucifer, from a mathematical room, signing off for tonight. Have a nice day.